Hi, everyone. If you're still filing in, that's totally fine. Obviously, there are plenty of seats this time. So I'm Abby Fuller. I work in developer relations for AWS. I hope you all enjoyed the keynote this morning. I'm really excited to have everyone here at the London Summit. This is advanced container management and scheduling today. So we'll mostly be focusing on ECS, but we'll also talk about some container image size tips that can apply to whichever orchestration tool you're using. So without further ado, since we are short on time this morning, what is container management and why should you care about it in the first place? So container scheduling is how your containers are placed and run on your instance. So that's pretty simple. A lot of these things are things that come kind of by default with whatever orchestration tool that you're using, but we can still get some customization out of it. So with containers, seems pretty simple, just a box full of whatever processes you're running there and their associated binaries and libraries, but there are still some moving pieces that go into there. So there's still some things that you can manage and optimize. One container is pretty easy, or easy-ish, but the more containers that you have, the more problems that you have. So think about having one container, and it's 2 gigabytes, and everyone has 2 gigabytes. But what you don't have is 50 times 2 gigabytes. So the more containers that you have, if they're really kind of big, the more problems that you have as you kind of scale. And think about how many problems you have if you're continuously deploying your 2 gigabyte container. So to avoid doing extra work managing these containers that we don't have to do, we turn to orchestration tools. So that's something like ECS or Kubernetes or Docker Swarm or Mesos, tons of options out there. But what these orchestration tools are for is helping us with all the tricky bits of container scheduling. So it's the scheduling, the managing, the deploying, and scaling, and resource management. And most orchestration tools have at least some level of built-ins to help you manage these things, but we have to do some of it ourselves. And in a lot of cases, we want to do some of these ourselves. Because when you build an orchestration tool, you build for like the 85%. So that this default is pretty good for almost everyone, but it's not always the best if you think you could optimize or if your use case is a little different. So we can tweak some of these things ourselves. So let's take a look at how some of these things work in ECS. Couple different types of schedulers. So you have your first one, which is, I think, probably the most commonly known one with ECS, and that's a service scheduler. You have a batch scheduler, an event-based scheduler, and then you can also run daemon processes, which are not quite a scheduler, but they serve, in a lot of cases, the same purpose. So a service scheduler manages tasks that are managed through a service. So that means that the service itself controls how many copies of a task are running, what your minimum number is, what your maximum number is, when I should add more, and then how I should place those on the instances that belong to my cluster. A batch scheduler runs many short-lived tasks in parallel. So an example of when you might use this is reading items off queue. So when a new item is added to the queue, start up a batch job to process all the items that are currently in the queue. An event-based scheduler runs a task in response to an event. So this is really similar to how cron tab works on Linux. So we'll take some sort of action every time a specific time occurs. So maybe that's every 12 hours, maybe that's every hour, maybe that's the third Tuesday of every month. A daemon scheduler runs a single copy of a process, and usually one per host. An example of this might be a logging agent or a monitoring agent or a sidecar process. So you usually want one and only one for every single host, but you run it outside of the service scheduler. So as part of service scheduling, you can also deal with your with your task management policies and constraints. So that means, how do I place my tasks? How do I not place my tasks? And what do I need in order to place a task there? So by default, ECS has some behavior that works for you. So it will spread tasks according to both availability zone and then by the least number of running tasks. So it'll spread them across the region, across the availability zones. So if I have 3 availability zones, it will try to spread one in each. But then it will also place by least number of running tasks, meaning it won't cluster all those tasks together on one host if it can spread them out. But we don't have to use this default behavior. So we can choose to, and it just works out of the box without us having to do anything. But if not, I can customize it. And this is how it works. This is, I feel like a middle school flowchart, but I made this myself. So if anyone's seen my PowerPoint art before, this is no different. So first up, I have to satisfy what I consider the hard constraints. So things like CPU and memory and sometimes port. And we'll talk about why it's sometimes port in just a second. Next, I can do my custom constraints. So that's a tag if I added a tag or a specific AMI. Then I select the instance that meets my policy. So that might be spread, so spread them evenly, or bin pack, or cluster them as close together as possible, and then pick the final instance that I want to place my task on. So let's go through these in order. And it's one of my greatest disappointments that I can't actually see that my GIF is working until it gets on the screen. So I am delighted to know that my GIFs are working. So cluster requirements are hard requirements. So those are defined by the instance type that you're using. So that might be memory or CPU or bandwidth. I promise we'll still talk about what sometimes port means in a second, and we'll talk about how to optimize those. But those are hard requirements. So things that I cannot make more of without either choosing a new instance type or rebalancing the tasks that I already have running. A custom requirement is a requirement that I choose myself. So an attribute or a label or an AMI, I can choose that myself, so I don't have to filter on them, but I can choose to. Here are some examples of what some custom constraints might look like. For example, a specific availability zone, or if I only want to run my message processing tasks on a certain AMI, I could do that this way. So a placement strategy is how I want my tasks to be distributed. So that's bin packing or spread. A couple of different examples of these. So we have 4 supported ones. So bin packing means to cluster as closely together as possible. So if I have two hosts that belong to my cluster, it will fill the first one as closely as possible before it moves on to the second one. Spread will try to distribute them as evenly as possible. Affinity means in like groups. So if I have task A and task B, and they always belong together, the scheduler will always try to place those together. Distinct instances is exactly what it sounds like. So it will try to place them only on separate instances rather than grouping them together. So you can start customizing these yourselves, so you don't have to use the default behavior. There are some templates that you can choose from, or you could write your own. And you can get pretty specific here, or you can pick from the drop-downs. So you can make these pretty much as specific as you want. So if you want to filter by availability zone and also by spread, and then also bin pack on top of that, and then also filter by an AMI, you can do this. I had someone ask me once, though, whether there was any behavior that would stop them from adding too many custom constraints. So would the scheduler at some point drop constraints in order to continue scheduling tasks? And the answer is no, so proceed at your own risk. So you can add as many constraints as you want, but eventually, if you add a lot of constraints, you will constrain yourself right out of being able to place any tasks. So let's talk about resource usage, which I think is everyone's second favorite topic, and your third favorite, I think, is networking, which, good news, we'll also talk about. So what do you do about resource constraints? So these are our hard constraints. So these are controlled by your instance, i.e. a C instance versus an M instance. The amount of memory and CPU that you allocate to your task is defined through your task definition. So in EC2 mode, colloquially known as just ECS, you can choose whatever instance type you want. With Fargate, you choose from a sliding scale of memory to CPU ratios. So this is an example of what it looks like in Fargate. I think it adds up to about 50-ish combinations of CPU to memory. And it's pretty generous. So I think you can get up to 4 virtual CPUs and up to 30 gigabytes of memory. So a couple options for you with EC2 mode. Choose whichever one you want. So port, technically a hard limit, as in if I have an app that's running on port 6000, I can't really do anything about that, right? In order to get more copies of port 6000, I have to start another instance. But I can use dynamic port allocation. So who here has worked with an application load balancer before? OK, so my favorite part of that load balancer is that you can do dynamic port mapping, which means I map to port 0 on the host, right? So all load balancers kind of do the same thing. So they distribute your traffic. So that might be between an IP address or an EC2 instance. It could be different tasks in a service. 3 different kinds. So number 1, ELB Classic. That's the original. Balances traffic. That is it. Next up is application load balancer. That's at the request level, which is layer 7. Great for microservices. You can do path and content-based routing, which means to route to something like /web or /API or /tasks. Only works inside of VPC. Third choice is network load balancer. It's at the connection level, which is 4. Routes to targets, so EC2 instances or containers or IP addresses. Good for high throughput, low latency. especially good if you have volatile traffic patterns. So that means that if you go from 0 requests to 100,000 requests, that would be considered a very spiky traffic pattern, requires no pre-warming, can just handle the traffic right away. I included a link, by the way, if you're getting the slides after this. I included a couple links as we go along that you can look at if you're looking at the slides later. So what do load balancers have to do with resource management? So 2 things. So first, the load balancer is what's actually distributing your requests. So if you're one of those people that sends me a message on Twitter and says, hey, my ECS deployments are slow and I don't know why, this is usually the first place that I'll tell you to look. Because a lot of your ECS settings can be tweaked at the load balancer level. So that's things like the connection draining timeout when you're scaling traffic off of a task. That's the cooldown period in your auto-scaling group before it adds a new instance and tries to execute the rule again. So a lot of your behavior for how quickly your deployments happen can happen at the load balancer. It's also health checks. So checking, for example, 15 times, 10 seconds apart before something is considered healthy or unhealthy, that slows your deployment down. So there's some load balancer settings that you can check that help not only with your deployments, but also with your resource management. And secondly, with port allocation and ALB, you can effectively remove one of your hard constraints, which is port. So this is binding to host port 0 and only passing in the container port. So if my container process runs on port 80, I can map to 80 on the container and 0 on the host, and then I can let the load balancer allocate it a port, which means that if I have a process that runs on port 8000 on the host, previously I would have had to spin up a whole new EC2 instance to auto-scale that task. I don't have to anymore because I can let it go to 0, and then both of those copies of that was effectively the same task can run on different ports, which means that I can wait just a little bit longer before scaling up, which lets me use my resources a little bit more effectively. So the importance of images. So this is not ECS-specific advice, although I guess some of it is. Also applies to Kubernetes or Fargate or Mesos or Swarm or whatever you're using. But a major component of your resource management is going to be how big or how small your Docker images are. So those add up really quickly, and they have really important consequences, right? Because I've been on call, and I've definitely been woken up on call. And I'm going to tell you the story, even though it's embarrassing, like all my stories, I guess. But if you make, for example, this really beautiful, well-organized, super well-commented Docker image that has many, many lines, and it's so beautiful and so readable, and you're such a gift to developers. And then it turns out it's actually quite large, like 6 gigabytes. And then you continuously deploy that. And now I have, because it's a startup and I deploy very frequently, very often, very quickly, I now have my 6 gigabyte image very generously strewn across my entire EC2 cluster. And then at 3 o'clock in the morning, my best friend PagerDuty is like, hey, you got no disk space left. I'm like, you mean on just one host? PagerDuty is like, no, you have no disk space anywhere. And that, my friends, is how continuous deployment plus a really bad Docker image woke me up. And you can learn from my mistakes. So you do not have to get woken up by this. So the more layers you have in general, the larger those layers are, the larger your final image size will be. This kills your disk space. And this actually kind of is opposite to how I would write regular code, right? Because with regular code, I might comment things out. I might spread things out into more than one line when it makes it a little bit more readable. That's the opposite here. So we're going to talk about how we can reduce these sizes a little bit. So number one, just like kindergarten, sharing is caring. So use a shared base image wherever you can. I said this to a couple of people after the ECS talks yesterday. Use a shared base image. Two, limit the data that you write to the container layer. So that means if you're doing something like downloading a whole library of data and you're using it for a little bit and then never touching it again, like populating a test database, get rid of that file in the same line. Don't write it back to the container layer. Chain run statements, which, yes, it makes it a little bit less readable, but also makes a much smaller image. And then lastly, prevent your cache misses at build for as long as you possibly can. And we'll talk about that in a second, too. Wu-Tang. So cache rules everything around me here. And this is a funny joke, by the way. So if no one laughs, I'll be disappointed. So calling run, add, and copy, they all add layers. So other instructions will not, assuming that you're on Docker 1.1 and above. If you're below that, this does not affect you yet. So how the cache works in Docker. You start backwards from the container layer. Docker looks backwards at all child images to see if they use the same instruction. So if they do use the same instruction, Docker will use the cache. For add and copy, which are instructions that you generally use to get files, a checksum is used, which means it'll check the checksum of the new file against the previous one. If the checksums match, it uses the cache. If they do not match, it breaks the cache. Other than with add and copy, Docker will look at only the string of the command. So the string of the command here is what does it actually say in the command, not what it's doing, but what is the actual literal string. So for an example, with apt-get update, there's a footnote here, which takes up its own slide because it's really outgrown a footnote. But so what happens if my command string is always the same, but I need to rerun the command? So an example of this that's really popular is git commands, where the address of your repository very rarely changes, but the content changes. So you can either ignore the cache, so you can pass no cache, or you can break it by changing the string every time. A really popular way to do this is with the timestamp. So by passing the timestamp, it will change the string every time, will explicitly break the cache, so it will pull from your Git registry every time. In the image itself, make sure that you clean up as you go. So if you download and install a package, and if you're going to just use it, you can download it, install it, use it, and remove it in the same line, and then that package does not get committed to the final image size. So anything that you use and download in the same line does not get committed to that layer. You can also take advantage of things that come for free with your operating system. So this is from apt-get, and there is always, every time I talk about this, someone that comes up to me afterwards and says, you did not include this package or this flag that's in my particular package manager. This slide is not an exhaustive list of all package managers and flags. I am thinking, though, about writing a backup talk that's just command line flags. And every time someone asks me that, we're just going to have 60 minutes of command line flags. And that's it. No GIFs, no pictures, just flags. So I'm thinking about it. But for now, all of my examples are just using apt-get. This is not even all the flags for apt-get, but just so you know, this is one of them. So OS built-ins. I can install my packages, I can update them, and then I can remove the list, which is where my package installations come from, because I've already installed that package. So I don't need the list anymore. It's the same as cleaning up all that when you download stuff from the internet and it comes in like a tar.gz. I don't need the tar.gz. Once I've used the file, I don't need the zipped version anymore, so I get rid of the zipped version. So the same thing applies for your containers and your EC2 hosts. Clean up after yourself. A couple different ways to do this on your system itself. So the first one is Docker image prune, and that will get rid of all untagged images. You can also use system prune, which will go one step further, and it will remove things like unused volumes. So unused in Docker's case usually means untagged. So if something's new, so if you go into your host and you say Docker PSA, and it lists a bunch of stuff, you end up with things that are untagged, that have like nothing in the tag column. You can clean those up with either image prune or system prune. You can also use third-party things. So most orchestration tools will do something called garbage collection. And that means cleaning up after yourself in the same case. So ECS and Kubernetes both have default garbage collection behavior, which means they'll do some of this stuff like cleaning up unused images and volumes and tags. You can go one step further. So there's a really nice third-party one. It's called Spotify GC. That runs as its own container, and you can set it to garbage collect on top of that, so clean up a little bit more aggressively. This is not container specific also, but one of the greatest culprits of using up all of the resources, and this is something that didn't used to come up that much, right? Because if I have a monolith, how frequently do I really deploy it? Probably not very often. And in a lot of people's cases, they were working on these deploys, and they'd be scheduling and kind of planning for these deploys for maybe weeks, right? And then you deploy it once. Hopefully it worked, and then you'd kind of go through all the stuff, and then you'd get ready staging all of your changes for the next deploy. But with microservices, a lot of us move to things like continuous integration and deployment, where I deploy probably 10 times the rate that I did before. So in my case, deployed several times a day. In some people's cases, several times a week, still many times a day. But with that comes a lot of kind of associated, for lack of a better word, garbage that you didn't used to have that many. So one part of this is all of your unused and untagged images and volumes. But the second part is stuff like logs. So if you have log rotate on, it's probably only going once a day, probably, if it's the same log rotate, at 3 o'clock every morning. But it only goes once a day. But think, if you deploy many times a day, think about how full your log files get and how quickly those log files get full. The same if you're using a package manager like npm is very chatty. So you ends up with lots of system logs, lots of Docker logs, lots of actual just stuff logs that are coming. And when you're deploying more and more often, you're getting more and more of these log files. So two kind of steps here. So one, you can change the system behavior of log rotate. So you can log rotate much more aggressively. You can rotate out more files. You can get rid of them every couple of hours if you're instead of every once a day. But what you can also do on top of that is that what I used to do with my system logs, too, is ship them off somewhere else as soon as I had them, and then I just removed the file after that. So I kept very little on the actual host itself, but all the logs, if I decided to care about them later, were all shipped off somewhere else. So there's lots of different ways to both kind of keep cleaning up after yourself and also reducing what's going on in your host. Because what I've also found with containers, too, is that the hosts change much less frequently because all of my actual changes are in the container. So the hosts themselves are also very prone to being full of kind of garbage and extra stuff because I'm not changing them very often. So they're full of things like old log files and images and other junk that I don't need anymore because all of my logs have gone somewhere else. And I'm probably many deploys of that container ahead of where I was. So that was all. If you're going to take anything away from this today, I think a couple things. So one, do me a favor. Take a pretty quick look at your Docker files, right? And that a lot of you might be doing something that I used to do myself, which is I downloaded just the operating system that I was familiar with, so like from Ubuntu or from whatever I wanted to use. But it can be a lot better than that. You can use language-specific Docker files, so like from Python, or you could use a more minimal one, like from Alpine. You can use that. Use something that's better for your actual use case. Clean up after yourself. Those really nice ordered Docker files where you've separated all of your run statements into different lines, you can change that too, right? So you can change how you're doing things. You can organize it maybe a little bit less good, but save yourself some space. Look at how often your connection draining is happening, how often your health checks are happening. But you can speed things up, and you can get a little bit more out of your infrastructure. But just take a look. Look through these Docker files, and I think everyone can maybe find a little bit that they can improve on. So we're not going to take questions out loud at this one because there's no mics, but we have time for 10 minutes of questions right down here like I usually do. So if you have a question, I'll be standing right there, and we can chat for a couple minutes. So if not, thank you, and there will be more sessions all afternoon for the London Summit. Thanks, everyone.